Go for it.
The question is, a second crazed physics student throws another pumpkin from the same place as student in number 4, but she throws hers up at 19.4 units per second. Determine the velocity of the pumpkin just before it strikes the ground below.
Okay, so we listed our knowns, and we knew the acceleration, which is just the constant of gravity, which is a negative 10 meters per second. And then we knew our initial because she threw it up at 19.4 meters per second. Of course, it's a positive direction because she threw it up. And if negative is down, so she threw it up at a positive direction with the 19.4 velocity, initial velocity. And then the delta y is, well, if the start is 0 and the bottom is 14.2, then the change is 14.2. And since it's in a negative direction, it's in a negative 14.2. So we knew all these three, and we're trying to find the final velocity. So we found an equation, which was Vf squared equals Vi squared plus 2a delta y. And so we just plugged in our numbers, and we got our initial is 25.7 meters per second.
Cool. Yeah, give him a big round of applause. Okay. Now, I want to show you guys yesterday's results side by side. So, thank you. See if we can lay this up here. The upside down board. That works. I just want to compare it to this one right here. Now, how did number 4 and 5 answers compare?
They both ended with the same answer.
They both ended the same answer. Right? Isn't that strange? All right. I just want to go into a short explanation as to why, because I want you to see the symmetry of nature. It's really cool how it works. Okay, so the question now that I want to ask about these two is, why does that work? Can anybody explain why? Either go for it first, and then I'll
try. Like, since it's going from a higher, destination, it's dropped from a higher spot, it's still increasing speed, and so it's actually going faster than the object that was thrown at
So one is thrown up at 19.4. That one, I believe, is thrown up. Number 5. And that one's thrown down at 19.4.
Yeah. Never mind.
All right, Lindsay, you want to go for it?
I think it was of why they were the same.
Yeah, why do they end up with the same answers here?
It's because the girl who threw it down, it had gained speed already, so it's already going fast. And the one that they threw up in the air, that one gained speed on its way down. So it went, technically the distance for the second one was farther than the one at first. So that's why it gained enough speed to go the same velocity.
That's right on the right track, Renato.
So when she threw it up at 19.4, so she threw it up at 19.4. So with gravity, it has the same ratio between because when gravity cancels it out, isn't it canceling out in the same ratio that it was accelerating in the first place? Because you have to give it time. So.
Yeah, it has to do with that ratio, just like Lindsay and Renato were saying. Okay, if we look at number 4, it starts off at 19.4. All right, here's our. Well, let's do the velocity this time because it's a little more like that. It starts off at 19.4 negatively and goes down like that. It keeps going faster and faster in the negative direction. Well, number 5, it actually starts up by going like this. Down more like that. So it actually starts at 19.4. All right. And then it continues on at 19.4. I'm going to make a note there. And then it continues on. All right. So when, like in number 5, here starts off at positive 19.4 going up. It has to do with the distances, like Lindsay was saying. All right, the area under a velocity versus time curve represents our displacement, or how far it goes, how high it traveled. What does this value here have to be to make these two triangles equal? These two equilateral triangles right there. Has to be what? 19.4. Okay, so once you throw something up, when it hits this point on its way back down, how fast is it going to be going? The same speed that you threw it up with. That's what that's saying. And so essentially the problem starts again right here, where these parts are exactly the same, like but now the rate changes at such a way. So when I throw something up in the air, and it comes back down, it's going to be going the same speed that I threw it up with. It's just a pattern in nature that occurs. I just think it's cool to make note of. It actually makes solving these problems easier if you apply that principle. Yeah.
So if you threw an apple with enough force that when it came down at the same amount of force is enough to kill someone, could you technically kill someone with that?
If there wasn't air resistance. It's a fun principle if there's not air resistance. It's the same way as like a bullet. You shoot a bullet straight up, and then it comes straight back down. It should technically be going whatever 2,000 feet per second. But the thing is, the air is it hits its terminal velocity, and lots of times it'll just burn up, or it'll just hit a speed where it won't kill you. But yeah, technically, if there wasn't air resistance, that could occur. But anything that you throw in the air is low enough speeds where when it comes back down, there's not going to be enough like terminal velocity. Like if I took this rock and just threw it up in the air, there's not going to be enough terminal velocity for it to actually matter. It'll come back down at the same speed you threw it up. So, anyway, I just want to show that principle, just a fun little principle of the way these things, of just nature. I just think it's cool to make note of. So, we good? All right, number 6. You're up.